Hi students, welcome to Govidya. As part of previous year questions, today also we are going to solve some more questions from the transformers. Okay. In between we taken some break due to some unavoidable reasons. Sorry for your miscommunication. Okay. From today onwards we will going to continue the sessions. Please share the links to your friends so that it will be helpful to them also for their preparation. Okay, let's start the session. The question is given about read the following statements. The Sumpner test is used to determine the efficiency of the transformer. Okay, the second statement is Sumpner test is used to determine the temperature rise of the transformer. Okay, just see what is the Sumpner test. What is mean by Sumpner test? We already discussed. We are going to take two identical transformers. We are going to take two identical transformers connected back to back. Okay. From this, what we are going to get? We are going to get iron losses as well as copper losses. If you know these iron loss and copper loss, you can calculate the efficiency. Okay, so the first statement is correct. Coming to the second statement, temperature rise. That means actual temperature rise. If you see the open circuit test or short circuit test, we are conducting the test separately. That means individually. So first iron losses may come, afterwards copper losses may come. But in Sumpner's test, at a time both losses will come. Okay, at a time both losses will come. So these losses are dissipated in the form of heat. Okay, these losses are dissipated in the form of heat. We can able to find out how much heat rise. Okay, how much heat rise is going to happen in actual because of the iron losses and copper losses at a time. Okay, so Sumpner test is be helpful for determination of the heat rise of transformer. So both statements are true. Is it clear? So our option will be both A and B. So it is a very simple question. If you know the concept of Sumpner test, then you can solve the question easily. Let's move on to the next question. The next question is given as, in a transformer, the EMF per turn in secondary winding is always less than the EMF per turn in primary winding. Okay, next statement you will see the EMF induced. We will write down here itself what they are telling. EMF per turn in secondary winding, that means E2 by N2 is always less than the EMF per turn in primary. The EMF induced in secondary winding is always equal to the EMF induced in primary winding. What they are telling, E2 is equal to E1. The EMF per turn in secondary winding always greater than the EMF per turn in primary. EMF per turn in secondary winding always equal to the EMF per turn in primary winding. Okay, these are the different options given, but if you see the options, in a transformer EMF per turn, that means E1 N1 equal to E2 N2 will be equal. Okay, so in a transformer, from the definition of transformer we can understood that E1 by N1 equal to E2 by N2. If you consider no load voltage drops and all, if you neglect it, then it will come like this. So among the given options, the best suitable option for the given question is D. Okay, EMF per turn in primary equal to EMF per turn in secondary, not direct EMF. If you see the second option, it will be little get confusing what to choose, B or D. So it is a very simple concept. uh, in a transformer there will be step down and step up transformer will be there. Okay, so step up means from lower voltage to higher voltage. From there itself we can understood that the primary voltage is not equal to the secondary voltage. But if you take EMF per turn in primary is equal to the EMF per turn in secondary. How we got this? From transformation ratio only. K is equal to E2 by E1 equal to N2 by N1. From this how we can write E2 by N2 equal to E1 by N1. Okay, is it clear? Let's move on to the next question. The question is given as, in a transformer, the self-induced EMF E1 and mutually induced EMF E2 are. Okay, they are asking about the phasor diagram and phasor relation between the E1 and E2. Okay, let's see the simple transformer operation here. I am considering at a no load condition. Okay, first we are applying some voltage from the source V. It will drawing current of I notch. Let's take it as a secondary winding. Let's take it as E2 and this is E1. Okay, whenever you are exciting a transformer with alternate voltage, then one flux will develop inside the core. Okay, flux will develop inside the core. If you see here phasor diagram relation, first take it as voltage phasor, applied voltage. The flux developed in the core will be 90 degrees lagging. Okay, 90 degrees lagging will be there. This is from Lenz's law. Okay, next current. Actually the transformer is drawing two components in no load current. What are those? First one is I mu, second one is IW. If you see the phasor diagram, this will be the I naught current. Okay, so similarly when the alternating flux is flowing through the core, self-induced EMF is E1 and mutual induced EMF E2 will develop inside the transformer core. Okay, E1 will be lagging the pi and E2 also will be lagging the pi. Why? Because the same flux is cutting this primary winding and the secondary winding. So these two will be in phase and lagging by 90 degrees with the flux. Okay, this is the phasor diagram of a transformer no load condition. So from this phasor diagram, what we understood, E1 and E2 are in phase. E1 and E2 are in phase. So our option will be A. Is it clear? Let's move on to the next question. The next question is about, read the following statements. They given different statements. We have to choose correct statement from the given options. An ideal transformer has no copper losses. Okay, An ideal transformer has no iron losses. Okay. An ideal transformer has no magnetic leakage. Okay. An ideal transformer has winding resistance. Okay. From the properties of ideal transformer, we can understood that it is no transformer is not having a winding resistance R, and there is no magnetic leakage in the magnetic leakage inside the transformer. That means R and X are equal to the 0. Okay, this is the properties of ideal transformer. When and one more is efficiency is 100%. This is the ideal condition. Okay, efficiency 100% means all losses equal to 0. All losses equal to 0. This is the ideal condition of the transformer. From the given option, if you observe, copper losses are not there. Yes, this may be true. No iron losses. Yes, it may be true. Third option has no magnetic leakage. Yes, it may be true. Fourth option, an ideal transformer has winding resistance. Okay. So if winding resistance is there, again copper losses will be there. Again efficiency may not be 100%. So it is violating the ideal transformer condition. So except D, all other options are correct. So let's select the given option. Our answer may be D. A, B, C only. D is not correct statement. Sorry. Okay. Let's move on to the next question. The next question is about transformer cores are laminated in order to. Okay. They are asking why you are laminating the transformer cores. So we already discussed eddy currents in a transformer. Okay, if it is a solid core, what is going to happen? If it is a solid core, resistivity will be less. Because of this, eddy currents will be high. If eddy currents are high, eddy current losses W will be high. So to reduce these losses, what we are going to do? We are going to do the laminated. That means this core is cut into small thin pieces and make it a laminated. Okay, we are cutting the core into small pieces and laminated. What we are going to get from this resistivity will be very, very high. This leads to eddy currents will reduce, then eddy current losses will be less. Okay, so our option will be minimize the eddy current losses. Okay, our option will be C. Let's move on to the next question. The next question is about the output of a transformer at full load and unity power factor is 400 kilowatt. Okay, what is the output at 0.8 power factor at half load? Okay, let's note down the given data. Full load output of a transformer at full load they given. That means in general output of a transformer will be given as VI cos pi. Okay, VI cos pi. What they given? P0. Let's take it as P output given as 400 kilowatt and power factor cos pi at EPF. That means 1. Power factor given as 1. What they are asking? Output at 0.8 power factor we need to, and half full load. They are asking half full load. We need to calculate. Let's see. Half full load means what is going to happen? Current is going to be, let's take it as PG. This is P01 and P02. Okay, let's take it as I02 will be I01 divided by 2. since they are telling half full load. Okay, let's take it as equation 1. Therefore P naught from equation 1, what you can write, Vi cos pi equal to 400 kilowatt. They given it as 400 kilowatt. I converted into watts. Cos pi they given as 1. From this what you can calculate, Vi is equal to 400 into 10 cube. Okay, let's take it as equation 2. Now we need to calculate P02 at the rate 0.8 power factor 0.8 power factor and half full load condition. What will be the formula? Vi cos pi, I is going to be divided by 2 because at half full load. Okay, from equation 2 we know the Vi value. From equation 2 we know Vi value. From that what you can write, P02 can be written as 400 into 10 cube divided by 2. Cos pi is 0.8. How much it will come? Let's calculate. 2 ones, 2 twos. Okay, 16. 160 kilowatt it will come. Let's see the options, what options they given. Our option will be A. Our option will be A. Is it clear? Okay, if you have the basic formula related to output power, then you can calculate the power at a given condition easily. Okay, let's move on to the next question. The next question is given about, read the following statements. An auto transformer has one winding only. Yes, we are in auto transformer, only one winding will be there. It will be acting as both primary and secondary. It is true. In step down auto transformer, power transformed inductively to the load equal to input into 1 minus k. Yes, this is also correct. In step down auto transformer, power transferred conductively to the load. Yes, this is also correct. In step down transformer, power transferred inductively to the load is k into input. No, it's not correct. Okay, it is not correct. So from the given options, only A, B, C are right. So our option will be B. Let's move on to the next question. Okay, the next question is given about a 25 kVA single phase transformer 2200 by 220 volt has a primary resistance of 1 ohm. Okay, primary resistance means they given R1 and secondary resistance is 0.001. Okay, find the equivalent secondary resistance. Find the equivalent secondary resistance. Okay, let's note down the concept. What is the concept behind this question is shifting of resistance, to secondary side. Okay, what is the formula we know? The equivalent resistance will be R2 equal to R2 plus R1 dash, where R1 dash is the shifted resistance from the primary. Let's take it as R02. Okay, R02 can be written as R2 plus R1 dash. What is R1 dash? R1 dash is equal to K square into R1, where K is transformation ratio E2 by E1. Okay, this is the formulas we know related to the shifting of resistance from primary to the secondary. What they are asking, equivalent resistance, equivalent secondary resistance, that is R02 we need to calculate. Okay, let's note down the given data. E2 E1 by E2 is given as 2200 by 220, and primary resistance R1 is given as 1 ohm, second resistance R2 is given as 0.01 ohm. We need to calculate K transformation ratio. It will be E2 by E1. 220 divided by 2200. It will be 1 by 10, 0.1. Okay, transformation ratio is therefore K equal to 0.1. So let's take it as equation 1. Okay, this is equation 2. We'll calculate from equation 2, we'll calculate R1 dash. What is R1 dash? K square into R1. 0.1 whole square into R1 is 1 ohm. 0.01 into 1. Therefore, that is called 0.01. Okay. From equation 1, okay, from equation 1, if you see the equivalent resistance in secondary side R02 equal to R2 plus R1 dash. R2 is given as 0.01. We calculated R1 dash as 0.01. Therefore, total resistance R02 is equal to 0.02. Okay. This is the equivalent resistance referred to the secondary side. So our option will be C. Our option will be C. Is it clear? Okay, let's move on to the next question. The next question is given as, in a transformer, no load current is made up of two components, namely magnetizing current IM and iron loss current IW. Magnetizing current IM and iron loss current IW. Okay, what they are telling, the relation between the phasor relation between IM and IW they are asking. Okay, with respect to supply voltage, we already discussed the phasor diagram under no load condition will be like this. First we are going to apply the voltage V. The flux generated in the transformer is going to lagging by 90 degrees due to the Lenz's law. Okay, due to the Lenz's law. So now the two components are there, magnetizing component and iron losses component. We know that iron losses component is directly proportional to the applied voltage. Okay, iron losses component is directly proportional to the applied voltage. This will be the IW. And magnetizing current is in normally magnetizing current IM is directly proportional to the pi. Okay, IM is directly proportional to the pi. So our IM will be in phase with the flux, and it will be far greater than IW. Okay, so what will happen? The equivalent phasor is no load current I naught. Okay, so from this if you see IM lags, IM means magnetizing current lags 90 degrees IM lags, okay. IM lags supply voltage by 90 degrees, supply voltage by 90 degrees, whereas IW is in phase with supply voltage, okay. So this is the statements we can draw from the phasor diagram. Let's see the given options. The given options is A is correct, okay. IM lacks supply voltage by 90 degrees and IW is in phase with the supply voltage, okay. If you are clear about the phasor diagram, we can easily solve this question. Let's move on to the next question. The next question is about, read the following statements. In a core type transformer, the core surrounds the windings. In a shell type transformer, the windings surround the core. Okay, let's draw the diagram of core type transformer and shell type transformer. This is core type transformer. This is cell type transformer. If you see the physical arrangement of a transformer, core type transformer, the winding, this is winding is surrounded by winding is surrounded by core. Core is surrounded by winding. We can write it as core is surrounded by windings, okay. So here in cell type transformer, winding is surrounded by core. Winding is surrounded by core. Okay, so if you see the diagram, what is going to happen? Core type transformer means core is surrounded by winding. Shell type transformer is winding is surrounded by core. Okay, our option will be A. Let's move on to the next question. The next question is about, in large transformers, tappings are provided on the high voltage side because, okay, what they are telling, in a large transformers, tappings. In general, if you see, the transformer winding is going to secondary winding. If you see HV side, this tappings will be provided like this. Okay, why tappings required? To change the secondary voltage. Okay, why only HV winding you need to choose means, HV winding will have the large number of turns. and low current. In HV winding it will be low current will be there. Okay. And easily accessible, since HV winding will be on top, easily can be accessible. Okay, easily accessible for repair. Accessible for repair. Okay, if you see, as the HV winding is having more number of turns, what will going to happen? So we can change the secondary voltage very smoothly. That means very small voltages also we can change. It will leads to better voltage regulations. If, as number of turns are more, it will leads to better voltage regulation. Okay, better voltage regulation we will get. Okay, and it is carries as low currents. While shifting the tappings, there is no sparking. Okay, since if it is high currents are there, if you are shifting one tap position to other tap position, there is a chance of arc formation in the winding. This may leads to sometimes severe damage to the transformer. Okay, since we are choosing HV winding, it will carry very less current. That's why the arc formation will be less. So it is safe to shift from one tap to other tap on load condition. Most of the tap changings are going to be done on load condition with the device called OLTC, on load tap changer. OLTC will be there in high voltage transformers. With the help of this, we are going to change the tappings. Okay, but these tappings we are going to change on load. That means current will be flowing in the winding. That time itself we are going to change. Okay, since it is, if you are choosing a high voltage winding, the current will be less. Thereby, that flashover inside the transformer will be very less. Okay, the given options, if you see, it has large number of turns which allows smoother control of output voltage. Yes, it is correct. It carries low values of currents. Yes, it's correct. It is easily accessible for repairs. Yes. In a transformer, if you see, on top of the core, first we are placing LV winding. Okay, first LV winding we are going to place. Why? The insulation required on top of the core, if you place LV winding, will be very less. Low voltage required, very less insulation. If you place HV winding, what will happen? It requires more insulation and the transformer will become bulky and cost of the transformer also will going to be increased. Okay, that's why always the low voltage winding will be first placed on the core to reduce the insulation cost and to reduce the size of the transformer. On top of that, again one more insulation we are providing. On top of that, we are going to provide the HV winding. So HV winding will be on top of the core, and inside LV winding will be there. If any repair or the trappings you have to do, sorry, if you want to do any repairs, HV winding is more accessible. Okay, it's true. D, it provides better voltage regulation. Yes, it will as the tap changing is very smoother in HV winding. It is voltage regulation will be smoother in condition. So all four options are correct, A, B, C, D. So our option will be B. Okay, let's move on to the next question. Read the following statements. Open circuit test is used to determine the core losses in transformer. Open circuit is, yes, open circuit test you are conducting to find out the core losses in transformer. Yes, it is true. Short circuit test is used to determine the copper losses in a transformer. Yes, this is also true. Short circuit test is used to determine the equivalent impedance in a transformer. Yes, it is also true. Short circuit test is used to determine the iron losses in the transformers. This is wrong. Okay, iron losses we are going to calculate at rated voltage. Okay, rated voltage, this can be possible only in open circuit test. Open circuit test. Okay, so among the given statements A, B, C are true, D is wrong. So our option will be B, only A, B, C. Let's move on to the next question. The next question is given about the following condition must be satisfied for parallel operation of a single phase transformers. Okay, the transformer should be properly connected regard to the polarity. Polarity, yes, it is true. If polarity is not same, what will happen? Circulating currents will be there. Circulating currents will be there. Circulating currents will generate. What will happen with this? The circulating currents will generate the heat, and there is a chance of blast of the transformer. So polarity need to be matched before connecting two transformers in a parallel. The next question is, the next statement is the transformers should be have the same turns ratio. Yes, both having the same turns ratio and same X by R ratio. If both are same turns ratio and X by R ratio, what will happen? Circulating current, first thing is circulating current won't be there if it is the same turns ratio, and X by R ratio same means both will be operated at the same power factor. Okay, same power factor. This is also true. The percentage impedance should be equal in magnitude. Yes, this is also true. If it is equal, the load sharing will be according to their impedance. Load sharing will be according to their impedance. Okay. The last statement is the transformer should not have the same turns ratio. No, if it is not same turns ratio, then circulating currents will form. It will generate heat inside the transformer. There is a chance of blasting of the transformer. So from the given options, the suitable options are A, B, C only. Okay, so our option will be B. Okay, let's move on to the next question. The next question is given about a 100 kVA transformer has a transformer loss of 100 watt and copper loss at full load are 400 watt. Calculate kVA loading at which efficiency is maximum. We know that at maximum efficiency, iron losses is equal to copper losses. Okay, iron losses is equal to full load copper losses, where X is the fraction of full load. Okay. From this X you can write as square root of iron losses by copper losses. Okay, from the given data, if you see kVA given as 100, iron losses are 100 watt, copper losses are 400 watts. Okay, so let's substitute the given values here. We will get iron losses are 100, copper losses are 400. It will come 1 by 4, it will be 1 by 2, so 0.5, where X is the 0.5. What they are asking? kVA loading. So therefore maximum efficiency, what I have to write here is kVA loading at maximum efficiency. Maximum efficiency is equal to X into kVA. What is the X we calculated? 0.5 into kVA is given as 100. So it will be 50 kVA. Our option will be D. Is it clear? So if you understand the formula of so not formula, if you understand the condition of maximum efficiency, iron losses is equal to the copper losses, but copper losses are varying with the load, so we need to consider the fraction x. Okay, in general iron losses Wi is equal to x square into full load copper losses. So from that we can calculate the x. X is a fraction of load at which maximum efficiency is going to be occurred. Okay, so they are asking kVA loading. kVA loading will be x into given kVA of the transformer. From that we calculated, we got the option D. Okay, let's move on to the next question. The next question is about transformers are rated in kVA instead of kilowatt because, okay, the rating of transformer is given in kVA not in kilowatt because. So if you see the transformer, the major losses in a transformer are iron losses and copper losses. Yes, the iron losses is directly proportional to voltage. Okay, iron losses depends on the voltage and copper losses depends on the current. Okay, depends on the current. There is no power factor, is not at all depends on these losses are not depends on power factor, not depends on power factor. Okay, not depends on power factor. So as the losses are mainly depends on voltage and current, the transformer rating is given as VA. The transformer rating is given as kVA instead of kilowatt. Kilowatt is nothing but VI cos pi. As power factor is not a depending factor for the loss calculation, so we are going to use the rating as kVA, that means V into I. So in the given options, the total transformer loss depends on volt ampere. Is it correct? Okay, other options also we will see. Transformer losses depends on phase angle, that means cos pi. No. kVA is fixed, whereas kW depends on the load power factor. No. Load power factor is often not taken. Okay, no. All other options are wrong, only option A is correct. As the losses are depends on voltage and current, it is not depends on the power factor. Transformer rating always given in kVA. Okay, let's move on to the next question. The next question is given about a transformer has negative voltage regulation when its load power factor is. The question is about voltage regulation. We know the voltage regulation curve. This is percentage regulation. This is versus power factor. Regulation versus power factor. The curve will be looking like this. Okay, curve will be looking this. This side will be lagging. This side will be leading power factor. It will be maximum for UPF lagging. It will be 0 for leading power factor. 0 for leading power factor and negative. From this voltage regulation curve, we can understood that. Okay, we can understood that percentage regulation of a transformer will be possible 0 and negative only for leading power factor. Okay, leading power factor. So our option will be A. Transformer has negative voltage regulation for leading power factor. From the voltage regulation curve, if you remember this curve, we can solve the question easily. Let's move on to the next question. The next question about read the following statements. While performing the open circuit test in a transformer, high voltage winding is open circuited. Okay, yes, it's true. Why? Because in low voltage side we can apply the rated voltage, so that the transformer is going to operate at the rated voltage. the losses will be calculated in accurate condition. Second option is given as performing open circuit test in a transformer low voltage winding is open circuited. No, if you open circuit at low voltage side, we had to connect the HV side to the source. HV side to the source means we need high voltage required to generate the rated losses. Okay, we already discussed what are the different drawbacks if you connect HV side to the rated voltage. We need a high rated equipments, measuring equipments required, and more losses will be there. Okay, these all are the drawbacks if you connect HV side to the source for calculating the no load losses. So this statement is not correct. Okay, this statement is not correct. What about the next statement? While performing the short circuit test in a transformer, low voltage winding is short circuited. Okay, short circuit test in a transformer, low voltage winding is short circuited. Yes, low voltage winding is short circuited. Why? Because in HV side, if you apply the source at HV side, very small voltage required to drive the rated current in the secondary side, that is LV side. This is correct. Option D is while performing the short circuit test in a transformer, high voltage winding is short circuited. No, this is not correct. Why? Because if you short circuit in a high voltage side, LV side is going to connect to the source. So LV winding voltage will be less, current will be high. So in order to drive the rated current inside the transformer, we need more current, and more current leads to the higher rated equipments for measuring, and more losses will also occur. This also some drawbacks are there. This is not recommended. So only correct statements are A and C. Our option will be D. Is it clear? Okay, next question is about read the following statements. Transformer transforms the voltage. Transformer transforms the current. Okay. Transformer transforms the frequency. If you see the transformer, what are the different properties? If you see, power will be constant. Okay, power will be constant. Flux inside the transformer will be constant. Okay, frequency will be constant. Okay, these three parameters will be constant at any cost, at any load. If frequency is variable, means what will happen? V by F ratio will be changed. This leads to B max required will be changed. Okay, this leads to high magnetizing currents. This may leads to high heat generation. Heat rise will be very high. This may leads to blasting of the transformer. So we need to maintain the frequency constant. Okay, that means V by F ratio need to be maintained constant. So in the given options, transforms the voltage. Yes, from step up to step down. If you see if you see the step up transformer, it is going to step up the primary voltage to secondary voltage. Voltage is going to be rise. Transforms the current. Yes, if you consider a step up transformer, the primary side will be low voltage side and current will be high, and secondary side voltage will be high and current will be less. Current is getting transforming. Okay, but frequency is not transforming. Frequency will be always constant. So our suitable options are A and B. Is it clear? Our suitable options are A and B. Let's move on to the next question. The next question is given about read the following statements. Okay, Sumpner test is used to determine. I think this question is repeated. Okay, we already discussed this question. the Sumpner test is used to determine both efficiency and heat temperature rise. Okay, our option will be both A and B. Okay, let's move on to the next question. The question is given about a 11,000 by 2200 volt 100 kVA single phase two winding transformer is used to connect an auto transformer by connecting two windings in series. Which of the following are not possible values, voltage ratios and kVA outputs of a auto transformer? Okay, kVA output of a auto transformer. So if you see the given voltage ratio is 11,000 by 200. The possible terms is, if 11,000 if you make it is a common winding, then 2,200 if we add up to this, how much it will come? 13,200. So the possibility is 11,000 divided by 13,200. One possibility. Okay. If you make 2200 as common voltage, it will be 11,000. So it will be 13,200. So the possible ratio is 2,200 divided by 13,200. Let's see the different options. Given. What are the different options given? 11,000 by 13,200. Yes, it is there. This is matching. Possible ratio is there. 2,200 by 13,200. It is also there. And 13,200 by, yes, if you make it is a step down transformer, this also is there. Okay, so almost all options are nearby, but kVA we need to see. Okay, auto transformer kVA rating we have to see. Auto transformer kVA rating, if you see, what will happen? We know that auto transformer kVA equal to transformation ratio K into otherwise you can calculate from the circuit diagram very easily. Okay, kVA can calculate from the circuit diagram. Wait for a minute. Okay, let's draw the circuit diagram for one case. Okay, any one case you will check if it is matching, means you can calculate the answer easily. Okay, the auto transformer will be like this. It will be, I taken it as a series additive circuit. I taken 2200 as a common winding. Okay, this will be the load. The total secondary will be 13,200. Okay, let's calculate the current. Current ILV is equal to 100 kVA they given, so kVA will be in primary side 100 kVA, voltage will be 2200, so current will be 45.45 amperes. In secondary side, HV side, the kVA need to be same in both sides, so then it will be 11,000. Okay, 11,000, it will be 9.09 amperes. So if you see that, it will driving the current 9.09 ampere. Therefore, load kVA can be calculated as 13,200 into 9.09. It will come around 120 kVA. So for 2200 by 13,200, the possible kVA is 120 kVA. Okay, 600 kVA is not at all possible. Okay, 600 kVA not at all possible. So our option will be, they are asking which of the following are not possible. Okay, our option will be D. For 2200 to 13,200 ratio, the possible kVA is only 120, not 600. This, see here, we may use step up or step down transformer. That means 2200 divided by 13,200 or 13,200 divided by 2200. We can use this auto transformer as a step up or step down both, but kVA will be constant. So from the given our calculation, what you got? So only 120 kVA only got for this voltage combination, 2200 by 13,200. So the option D is not correct. Okay, this is about the today's session. By this we are going to wind up the session. Okay, if you have any doubts, please chat over the comment box. We'll come back to you. Okay, we are here to help you. Okay, as Govidya, we are providing test series and offline coaching center, offline coaching, online coaching also we are providing. Okay, if you are interested, if you want to get succeed in your upcoming competitive exams, be prepared with your preparation. Okay, we are ready to help you in your preparation at any manner. That means if you are strong at basics, let's go with the test series. Okay, with if how many questions you practice, that much confidence you get to write the competitive exams. So the success rate also will be more if you are practicing more questions. Okay, thank you. By this we are going to wind up the session.